Hello, everybody. This is Nighttime Mathematics Radio, coming to you live from our secret headquarters by the bay. Let's see. As always, this works the same way. If you haven't been here before, all you have to do is you tweet your math questions over on Twitter to @NightMathRadio, and I'll try to answer them live on the air. This is Nighttime Mathematics Radio. So let's wait for a few minutes here while we have a chance for people to chime in on Twitter. This is Nighttime Mathematics Radio. everybody. Apologies for having a little bit of technical difficulties tonight, as you can probably tell by the fact that we don't have the usual triangle showing up. But that's okay. We can at least get our camera. So let's talk some math. Now, Twitter's just about silent tonight, so let's take a look at some problems that came in over the week from other sources. Now, one question that came in, a calculus student was wondering about that dx that appears in definite integrals, wondering what exactly that's doing there. Let's talk about that. It's a little too zoomed in. Let's zoom out a little bit. Oops, that's zoomed in even more. There we are. That's a reasonable amount of zoom. Focus in again. There we go. Now, the question comes in, when you have a definite integral, for example, the integral from, say, 0 to 3, x squared dx, the question comes in, what's that dx doing there? What does that represent? Is it the same dx as in Leibniz notation? And how does that make any sense? And the answer is it sort of is the same dx from Leibniz notation. But what it's doing there is actually interesting. What it's doing there in some sense is making the units work out. So what is x squared dx? Or what this is the area under the curve. So we draw a little x squared, where x squared is just a nice parabola opening up like that. So 0 to 3, say. So here's 3, here's 9. Our x's aren't to scale, and that's fine. We're just in that curve, right, that area right there. And remember, when you first introduced integrals, what you started looking at initially was what are called Riemann sums, where you sat down and looking at, for example, we could take triangles looking at taking the left of each integer point. So we could say, okay, well, here's one rectangle at 0 with height 0, so that's got no area under it. Then at 1, we could take another rectangle of height 1. At 2, another rectangle of height 4, because this is, again, these points are 1 and 2, so this is x squared, so this is 1 comma 1, that's 2 comma 4. And we can say, well, what is the area? Well, the area is going to be the sum of I is equal to 0 to 3, or actually 0 to 2 in this case, right? Because there's 0, 1, 2 rectangles of the height, which is I squared, times the width, which we could call, say, delta x, which in this case is 1. So this will be 0 times 1 plus 1 times 1 plus 4 times 1, which is equal to 5. And we say, okay, that's 5 square units. Okay, well, what if we use twice as many rectangles? What if we have another one at 1/2, 0.5, another one at 1.5, another at 2.5? And we can do that sum as well. We can say, okay, in this case, we'll have the sum from I equals 0 to 5 of I over 2 squared times delta x, which in this case will be 1/2. So now you'll have 0 times 1/2 plus, when I is 1, you have 1/2, and 1/2 squared is 1/4, 1/4 times 1/2, plus, we have now, at 1, we have 2 halves squared, which is 1 times 1/2, plus, here we have 3 halves squared, which is 9/4 times 1/2, then 2 squared, so 4 times 1/2. Then finally, at 5, we have 5 halves, or 25/4 times 1/2. So we can add these terms up. The first term is 0, second term is 1/8 plus 1/2. So, and we can see that eighths is going to be a common denominator here, so I'll just write everything in eighths. This is going to be, so here we have 1/8, here we have 1/2, which is 4/8, plus here we're going to have 9/8, plus here we're going to have 16/8, here we're going to have 25/8. And we can sum all those terms up. We get 1 plus 4 is 5. 5 plus 9 is 14. 14 plus 16 is 30. 30 plus 25 is 55. So we have 55/8. And we can work out what that is. Let's grab a calculator and see what that is. That's now going to be, clearing last week's work, 55 divided by 8. That's going to be 6.875. Now, what's the integral actually going to be? Well, remember, an integral is just an antiderivative, so that's going to be 1/3 x cubed, evaluated from 0 to 3. So the correct answer is going to be 3 cubed, which is 27 thirds, minus 0 thirds, or 27 thirds. 27 thirds is 9. So the correct answer to this problem is 9. And we're creeping up on it. We've gone from 5 to almost 7. And as we keep getting more and more accurate, this is going to get closer and closer to the correct answer. Now you notice what this piece is. Here you have the function, f of x, evaluated at each point, times a delta x. And that delta x gets smaller and smaller and smaller. So the idea of a Riemann sum is that the integral from over some interval, say 0 to 3 f of x dx, is equal to the limit as delta x goes to 0 of all possible sums, I equals 1 to some number n, however big an n you like, of f of x sub I, with x sub I some point on the interval, times delta x sub I. And as you let those delta x sub I all go to 0, as you let them become infinitesimally small, those sums converge to the actual definite integral you're interested in. And that's what that dx is representing there. This is again indicating that a limit process is taking place, that what were finite sums are going to become an integral over infinitesimals in the limit. And that's what that's doing here. This is Nighttime Mathematics Radio. So let's pause again to see if anyone comes in on Twitter. If you have any questions, or you can tweet at nightmathradio.com and we'll try to answer them live on the air. Sorry, at nightmathradio. Once again, this is Nighttime Mathematics Radio. If you have any questions, feel free to tweet them to @NightMathRadio on Twitter, and I'll try to answer them live on the air. This is Nighttime Mathematics Radio. Welcome back, everybody. Let's now, for the second part of the show, let's talk about one of these questions that has Twitter in a permanent uproar. And it's an extremely silly question, so let's take a look at it. The question looks like this. And you see it all the time on Twitter. It comes around roughly every 5 minutes. Somebody asks a question like this. How do you evaluate this expression? 8 divided by 2 times the quantity 2 plus 2. Now, I'm going to talk about how to solve this problem according to math books, and then I'm going to talk about why this problem is very, very silly. Now remember, according to math books, you evaluate things according to GEMDAS. Sometimes they write it as PEMDAS, but I prefer to the G. This is this mnemonic you can use to remember what order operations go in. It's more confusing than it deserves to be, but the idea is you first do grouping symbols, then you do exponents, then, and this is things that get confusing, you do multiplication and division as they occur from left to right in the expression, then finally you do addition and subtraction as they occur from left to right in the expression. So according to math books, what you should do with this problem is first evaluate what's inside the grouping symbols. That's the parentheses here. So that's 8 divided by 2 times 4. Now remember, there's no difference between multiplication by adjacency and multiplication with a multiplication symbol. According to algebra, those are just both multiplication. So now, all we have left are multiplication and division. So, since those are at the same level of priority, we proceed from left to right across the problem. So this becomes 8 divided by 2 is 4 times 4, which is 16. That's, according to a math book, the correct answer to this problem. But there's a problem here. This is very silly. Why do I say it's silly? The reason is you essentially never, in actual practice, write long chains of multiplications and divisions like this. It doesn't occur. You never find yourself saying this times this divided by this, now times this times the... It doesn't come up. And because it doesn't come up, the rule that we said there of evaluate things from left to right is totally unfamiliar. That's why this problem is confusing on Twitter. People look at this and say, well, I don't know how I'd evaluate that. I'd never see something like that in real life. And the answer is, no, you wouldn't. Nobody would ever see something like this in real life. In fact, it's worse than that, because remember I said G here. You might be wondering, why didn't I write parentheses? And the answer is, there's another grouping symbol, and that's a fraction bar. So if I wrote this slash just a little bit bigger, like that, now the answer changes, and that's a disaster. That's why people don't write math this way. Because now that I've written the slash to be very large, it becomes a fraction bar, and a fraction bar is a grouping symbol. You evaluate everything in the numerator, you evaluate everything in the denominator, and then you divide. So with it written this way, which you notice looks almost exactly like the original thing I wrote, this is now 8 over 2 times 4. So that's 8 over 8, which is 1. This is why nobody in their right mind writes mathematics this way. Because it's genuinely ambiguous. You should never. The answer to a math problem should never depend on how slashy you've written the slash. That's disastrous. You might think, well, maybe it'll be better if I wrote a division symbol. But that's in some sense worse. Nobody's ever seen a division symbol since 3rd grade. This is not something that occurs in regular use. So the correct answer to this problem is, that's a bad way to write that expression. If Twitter can become inflamed by an expression, it doesn't matter which way is formally correct. It doesn't matter if the answer technically is 16 and not 1. You've written your mathematics badly. How should you write it? Well, you should take advantage of that grouping symbol. You should, moreover, not try to write everything on one line. So if you're forced to, because you're on a computer, you should use more parentheses to make it clear what you intend. You should either write 8 divided by 2 times 2 plus 2, which is very ambiguous. Sorry, very unambiguous. Now it's very clear what you want. It's 4 times 4 is 16. Or you should write 8 divided by square parenthesis 2 times 2 plus 2. And again, now things are unambiguous. Anyone who looks at it can look at that and say, oh yeah, it's 1. Your goal in math is not to be confusing for fun and profit. Your goal in math is to be clear about what you're trying to say. Math is just a language to express an idea in. The same as English, the same as anything else. So you should never write math in such a silly way as this original expression. In fact, better yet, if you have a real sheet of paper in front of you, or a real computer that can typeset equations, you shouldn't be using a slash anyway. Why are you trying to save lines of paper? That doesn't make sense. I mean, this made sense back in the typewriter days when you couldn't set an equation without pain and suffering, but at the moment this is really easy. If you want to set this equation properly, you can write it as 8 over 2 times 2 plus 2. And now no one will wonder what you mean. Or you can write 8 halves times the expression 2 plus 2. And again, no one will wonder what you mean. Either of those expressions is perfectly clear. So again, mathematics designed to trick people, even if you can get a fun problem out of it, is worse than useless. That's not what math is for. Math is for expressing an idea. It's for expressing a relationship. It's for expressing what you're trying to say. And if you're being confusing, you've written your mathematics badly, even if you can dig out a technical formal correct answer. This is Nighttime Mathematics Radio. And with that, I think we'll sign off. I don't think we've got any further questions on Twitter. So, good night, everybody. Happy mathematics, and I'll see you all next week. This has been Night Mathematics Radio. Good night.